Bismillahirrahmanirrahim. Welcome to the channel. My name is Asim Amjad. In this video lecture, we discuss the stresses in a C bar. Actually, the C bar is made of an alloy steel and it is used as a dynamometer, or a dynamometer is basically a device that is used to measure the magnitude of a force, let's say P. So, a strain gauge is usually attached to the surface of a location as shown on the screen, and the measured strain is used to calculate the force P. So, in this video lecture, we will create a 3D solid model for the C bar and then perform a static structural analysis under a force P, that is 2000 Newton, and then we will examine the stress straits at two locations A and B. We examine the location A since it is where the strain gauge is situated and its normal stress sigma y is high, and in location B is arbitrarily chosen for its non-zero shear stress tau hy. So this lecture tutorial is also demonstrate a way how to obtain the stress result at specific location, namely using the sensors. Okay, let's start the video and first launch the Solidworks and create a new part. So move to the new button, click on it and then select the part and click OK. After opening the modeling environment of the Solidworks, change its unit to millimeter setting. So move to the status bar and click edit document units. Then move to document properties and under the units select mmgs and under decimal select none and then simply click OK. Okay, now we are creating a sketch for the swiping path. So move to the sketch, click the front plane and click this sketch button, and the front plane is now normal to the view. Then move to the sketch tab and click this line button and create a sketch like this. Then move to the smart dimension and apply dimensions. 60, 100, and the radius is 10. Now click this point and this point and click vertical relationship, and now exit the sketch. So now you create the sketch 1 for swiping the part. Now we are adding a new plane and then create the sketch 2 for swiping the profile. Okay, so in that case move to the feature, click the reference geometry and click plane, and then first select this line and then select this point. So basically the line is used as the first reference and the point is used as the second reference, or a plane is normal to the first reference and passing through the second reference will be created, and then simply click OK. Now we are going to create a sketch for the profile. In that case move to the sketch and click the sketch and change its orientation to normal view and then draw a sketch like this. Now add in some relations. Now add the dimensions. Now add the fillets of 3 millimeter. And then simply click OK. And OK, and then simply exit the sketch. Now you see this point should be pointed over there. So first exit the sketch, click this point, this point, okay. So now the path and the profile is created. For using the sweep feature of SolidWorks, move to the features tab, click swept boss base. So for profile, select the sketch 2, and for path, select the sketch 1, and you will see or notice the preview on the screen. So the solid body is actually created. Then simply click OK. Now hide the plane, and the half of the C shape part is ready. Now we are moving to create an ear. For creating the ear of the C shape bar, first click this swept feature and click hide. And then select the front plane, click exit sketch, click the normal view, and then create the sketch like this. Now add some smart dimensions. The distance from this to this point is 100. And the length of this side is 30 millimeter. The radius of this circle is 20. And the length of base is 70. Add a small circle at the center, and the radius of this circle is 10. Sorry, the diameter of the circle is 10. OTG. So after completing the sketch, move to the features tab and click the base boss option. Select the mid plane, and the distance of the sketch is 5 millimeter. Make sure the merge result is checked, and then simply click OK. Now show this part. Okay, the issue is actually highlighted here. The The sketch 1 should be horizontal at these 2 points. Okay, now simply click this close sketch button, and here you will see the issue is resolved. Now click the extrude base boards, select the sketch, click mid plane, select the distance of 5 mm and make sure merge result is checked, and then simply click OK. Okay. Alright G. Now we are adding the fillets. So move to the fillet and select this edge and this edge, and the radius of the fillet is 3 mm. And then simply click OK. Alright, now we mirror the body. For mirror the body, move to the linear patterner and click mirror. And for mirror face or plane, select the top plane from the part tree, and under bodies to mirror, click this body and then simply click OK. Alright, our part is now ready for the simulation study, and now we first create the sensor at location A, that is here at the center of this length. So for adding the sensor, first move to the feature tab, and under the feature tab move to the reference geometry and select point, and then click this face and make sure the center of face is checked, and under the selection face 1 is selected, and then simply click OK. Basically this point 1 is the location where we set up a sensor, and this is the our point or location A. Now right click the sensor and click add sensor, and under the sensor feature manager select the simulation data, and under data quality select stress and sigma y normal stress, or we can also change it later on, this data quantity, and then make sure the properties should be in Newton per millimeter square or megapascal, and it shows the average of selected entities, and here select this point 1 from the part tree and then simply click OK. Alright, now we create a sensor at location B. For creation of the sensor at location B, first select the front plane, change its position or orientation to normal view, then move to the sketch and select this point and add sketch somewhere, then click the smart dimensions and add the couple of smart dimension. The height of this point to the origin is 70, and the horizontal distance from this point to the center is 110. Alright, click this exit sketch button, and now again move to the features tab. Under the reference geometry, click the point and select this point. Make sure one point is selected here and the point is selected at under the selection menu, and then simply click OK. Alright, now our point 2 is added here, and this is what we call location B. Now again move to the sensor, right click on it and click add sensor, and under the sensor manager select the simulation data. Make sure here the stress is selected and the normal stress for y direction should be selected. Properties would be Newton per millimeter square megapascals. Here select the average of the selected entities, and under the point selection move to the tree manager and select this point too, and then simply click OK. Now save this model as C bar. Alright, now we create a static structural study and set up the unit system. So make sure the simulation tab is already loaded, and in the simulation toolbar select the study advisor and click the new study, and under the study manager name this study as static force 2000 Newton, and make sure under general simulation this static button is checked, and then simply click OK. Now move to the simulation tab and click these options, and make sure under the options the length slash displacement unit in millimeter and the pressure slash stress unit is Newton per millimeter square megapascal, and then simply click OK. So in the study tree right click the C bar and click apply edit material, and under the material window select the alloy steel for the model, click apply and close. Now we are creating the mesh. For creation of the mesh, move to the mesh, right click and select the create mesh button, and this will open the mesh window and feature manager window, and leave all the setting as by default, and then simply click OK. So this is the default mesh. In general, the finer the mesh, the more accurate the solution. So let's make the mesh more finer. So for making the mesh more finer, again move to the mesh, right click and click create mesh, and under the mesh density move the scroll button to the last. So this is an easy way to refine the mesh, and then simply click OK. It will take some time. Okay, now we will use this mesh for this simulated study. So for seeing the mesh detail, simply move to the mesh, right click on it and then click the details. So the more details of the mesh is available under the mesh detail window, and here you will see the total nodes are 1,02,695 and the total elements are 62,636. Your numbers may not be exactly the same as here. If you don't create a mesh, the program will automatically create a default mesh right before solving the model. Okay, simply close this window, and now we set up the boundary conditions and run the model. So for setting up the boundary condition, move to the fixtures, right click on it and then click fix geometry. So move to the model environment and select this face, cylindrical face, and then simply click OK. Now move to the external load, right click on it and click force. And for force, add in the force, click this cylindrical face and then move to the force start feature manager tree. Make sure the phase 1 is selected and then move to the setting radio button, that is the selected direction, and under the selected direction select the top plane from the part tree and it is used as the reference coordinate system. Then move to the force section and click this normal to plane button and type it here 2000 Newton and then click reverse direction and then simply click this OK button. So the direction of the arrows show the force is adding or applied at this direction and this point is fixed. So after setting up the boundary condition, move to the simulation tab and click run this study button. It will take some time. Alright. Now move to the fixtures, right click on it and click hide all and the external load and click hide all. So now we hide all the fixtures and external loads and then move to the result section and under the stress one right click and then click edit definition and change the stress from von Mises stress to normal stress y, sigma y, normal stress in under the y direction and then click OK and then again move to the stress 1 section and click this animate button. On the screen you see the animation of the C bar while applying the force. So after seeing the animation, simply click this OK button and now we will explore the stress at location A and at location B. So first we explore the stresses at location A. For seeing the stress at location A, slightly move this window downward, scroll up and move to the sensor section, expand it and here you will see the stress at point A, that is around 56.78 Newton per millimeter square megapascal. Okay, right click the stress 1 button and click the edit sensor. And here you will see the sensor feature manager is pop up and now change this stress component from Y to S direction, normal stress sigma X, and you will see the stress value at point A is 0.000473 around megapascal. So we can say the stress value at stress component at sigma X is 0. Now we can also explore some other normal stress value. In Z direction this value is also 0. Now let's change the stress component value to the shear stress in XY direction and here you will see again 0. So you can explore on your own all the stress component in XYZ or shear stress in XY, YZ or ZS direction and you come up with this solution value that the stress values acting all the stress component are or would be equal to 0 rather than normal stress that is acting in the y direction, and that value would be probably 56.78 megapascal. So these are the stress component values at location A. Okay, now let's move or explore the stress values at location B. So simply click OK this sensor value and then move to the setting stress, that is the stress 2. Right click on it and click edit sensor, and here you will see the stress value at stress component sigma y would be 22.77 megapascal. Now let's change the stress value into the x direction, and the value is 94.87 megapascal. Now let's change its value to z direction, and here you will see 0 stress value is acting at location B. Now let's change its value to in xy direction, and you will see the opposite stress is acting in the xy direction. Shear stress is acting in the xy direction, that is minus 18.95 megapascal. You can explore the rest of the shear stress value, and you have to simply repeat the step to obtain the other stress values, and your result may not be exactly the same as here. And you can also note that the z components sigma z, shear stress in yz or shear stress in zx direction are all zeros. It is called a plane stress state, and the stress states that is discussed in this lecture are all plane stress states. Okay, now save the document and exit the Solidworks. Thank you.